Hi, I'm Aditya. This is my lab report for Lab 1, Charged Tapes. The purpose of this lab was to observe the interactions between charged objects and to estimate the amount of excess charge on a piece of U-tape. By the end of this experiment, I calculated the charge on the tape to be approximately 1.63 times 10 to the negative 8 coulombs. To do this, I relied on two fundamental physics principles. First, Coulomb's law, which relates electric force to charge and distance. Second, Newton's second law, specifically the concept of equilibrium, where the net force on a stationary object is zero. For the experiment, I created two charged U-tapes. I observed that they repelled each other, indicating they held the same sign of charge. They were also attracted to neutral objects like my hand, due to polarization. To find the magnitude of the charge, I floated one tape, tape B, above the other, tape A. In this model, I treated tape B as my system and tape A plus the Earth as the surroundings. Since tape B was floating motionless, the downward force of gravity was perfectly balanced by the upward electric force from tape A. Here represents the data I collected. My tape length was 0.2 meters. Given the density of clear tape is around 1 gram per meter, the mass of my tape was 0.0002 kilograms. The critical measurement was the separation distance. When tape B began to float, the distance between the tapes was 0.035 meters, or 3.5 centimeters. Using this data, I performed the calculations. First, I found the magnitude of the gravitational force using F equals m times g. This came out to 1.96 times 10 to the negative 3 newtons. Because the tape is in equilibrium, electric force must be equal in magnitude. So, the electric force is also 1.96 times 10 to the negative 3 newtons. Using the equation derived from Coulomb's law, I solved for Q. The magnitude of the charge on the tape was calculated to be 1.63 times 10 to the negative 8 coulombs. I also calculated that this represents a deficiency of about 1.02 times 10 to the 11th electrons. When compared to the number of atoms on the sticky surface, this means roughly 1 in every 3.7 million surface atoms lost an electron. I also created a computational model using GlowScript to verify this. I modeled the tapes as single point charges located at their centers. The code balances the gravitational force vector against the electric force vector. As you can see, the program output matches my hand calculations exactly, confirming the magnitude of 1.63 times 10 to the negative 8 coulombs. To make these calculations possible, I had to make two major assumptions. First, I treated the long tapes as point charges, with all charge concentrated at the center. This simplifies the complex integral of a line charge into a simple algebra problem. Second, I assumed that each U-tape had the same amount of charge. Since I made them identical, this is a reasonable estimation. I did not need to model air resistance, because my tape was stationary in my final observation. Finally, let's address some conceptual questions. What if electrons had a positive charge and protons had a negative charge? My observations would not change. The tapes would still have like charges even if the sign flipped, and they would still repel each other. They would also still attract neutral objects because polarization works regardless of the sign of the charged object. Why is it important to handle the tapes as little as possible? Our bodies are conductive, so when we touch the sticky part of the tape, electrons transfer between our skin and the tape. This effectively grounds it, and what this does is that it neutralizes the tape and ruins the experiment. In conclusion, the experiment successfully demonstrated the strength of electric forces, allowing a tiny amount of charge to overcome the force of gravity. The main source of error was likely the difficulty in measuring the fluctuating distance d while the tape was floating. Thank you for watching.